In this video, we'll talk about one way that you can use to distinguish between ohmic and non-ohmic materials. So I'm going to start with a graph. And I'm going to do a similar graph on this side to show you the difference. Alright, now what I will plot is a potential difference and current. And I will do the same thing here. Now, this is the difference between ohmic and non-ohmic materials. We know from Ohm's law that delta V, if Ohm's law is valid, delta V equals IR. Now, if you make this to be your y variable and this to be your x variable, then essentially you can see here that you have an equation of the form y equals ax plus b, where b is exactly 0. Now, what this means, if you have any object, let's say, I'm gonna do a drawing here. So I have a black box and I don't know what it has inside. Okay, well, in this case, it's a white box. So I have this, and I have no clue what it is. What I can do is place the two electrodes of a voltmeter and measure the delta V between the two sides. And then I can place an ammeter here. This would be your ammeter, where you can measure the current that flows through the device. Now I can change the potential difference and I can measure the current, and I can change the delta V again, a new value, and measure the current. What that will give me is something like this. Okay, I change delta V and I get a current experimentally, more or less something like this. Now, okay, experimentally I'm talking about. Now, when you have that, if it looks, and it does look, that it's a straight line, essentially the relationship between delta V and I, then you can say, well, what I'm gonna do the fit, and here from this I will find the equation ax plus b, and when you do that, you're actually finding the resistance R times I. Your b should be roughly 0, and a, the number that you get for a, is the resistance. So when this is made from ohmic materials, the relationship between delta V and I is going to be a linear one. Now, in contrast, when you have a non-ohmic material, you're gonna get something else. For example, say I have something similar, but now instead of, say, we have now an orange or a yellow, whatever this is, I have a different box and I don't know what it is, and I do the same thing. I measure the delta V across it, I measure the current that goes through the device, and then I use those pair of numbers to plot them. Now, okay, you get the idea. What if you get this kind of graph? Okay, obviously you cannot model it as a straight line because it is not. Okay, and I don't know how you will decide to model it. I'm just giving you an example. if you see that the relationship between delta V and I is not a linear one, then what you have is a non-ohmic materials, non-ohmic objects. They do not obey Ohm's law. And it is important to remember that not all objects obey Ohm's law. Okay, if I give you a resistor, what we call resistors, then those are made from ohmic materials, and they are made so that we can use this relationship when we work with circuits. If I give you a light bulb, on the other hand, and I ask you to do this kind of graph experimentally, delta V versus I, you will see that the relationship between those two quantities is not linear. And this is telling you, for example, that a light bulb is made from non-ohmic materials. And an example here would be resistors. A resistor. So this is how you can distinguish between the two types of materials. And I do want to mention one more thing before I finish this. You can see as the current increases, the slope of the line increases as well. And when you get your experimental measurements, you can see what happens when I increase the current. Okay, it is not a linear relationship, but what is it? And in this case, you can see that as the current increases, the slope also increases in the graph.